This is the first of two lectures on physical properties of nuclei. This lecture will focus on the properties and some simple models for understanding the patterns in those properties as the number of protons and neutrons in the nucleus are changed. And the second lecture, which will be the next one, of course, is going to deal primarily with concepts related to radioactivity and decay and nucleosynthesis. So here's the big summary. First of all, virtually everything that we can see is made up of three fundamental particles: the up quark, the down quark, and the electron. We have no evidence that any one of these three particles is actually made up of any other particle. Early in the development of nuclear and particle physics, it was thought that the proton and the neutron and the electron were the fundamental particles, but there were discovered patterns in the energy of particles that were observed when energetic protons and neutrons were slammed into one another and electrons were slammed into protons. The particles that came out suggested that protons and neutrons were actually made up of more fundamental particles, the quark. So the simple message here is that there are really only three particles, and then there will be three particles with mass that are of any relevance to normal matter, and the interactions between those particles require other particles, bosons, to carry the forces, and we'll talk about that in 2 or 3 lectures. So all the elements that we observe come from the ways in which these three particles combine with one another and interact with one another, according to rules dictated by the strong force, the electromagnetic force, the weak force, and gravity, plus the ideas with respect to statistical occupation associated with bosons and fermions that we've learned earlier in this semester. The strong, the weak, and electromagnetic forces are explicitly included in the Standard Model, which we'll discuss in a few classes. Gravity has not yet been incorporated. It is a very complex problem. So let's start with a statement about the nuclear properties. What do we know? And then the next thing that I'll do is talk about a little bit about how we know. Number one, the size of nuclei is very small. They are small compared to atoms. The Bohr radius is about 1/2 angstrom, and the radius of a nucleus is about 10 to the minus 5 times that. So it's 10 to the minus 15 meters. Bohr radius, 10 to the minus 10 meters. The nuclear radius, 10 to the minus 15. So it's essentially a point at the center of an atom. Charge. Nuclei have charge. And that charge, to the best of our ability to measure, is an integer multiple of the electron charge, except that it's positive. So it seems as though the charge on the electron and the charge on the proton, which carries the positive charge, is a very fundamental quantity, and we'll come back to that later on. Mass. Nuclei have masses that are nearly integer multiples of the proton or neutron mass. The mass of the proton and the mass of the neutron are nearly equal to one another, and that mass is about 2,000 times larger than the electron mass. The total mass of the nucleus is about twice the atomic number being the number of protons in the nucleus, times the mass of the protein. So twice that atomic number times the mass of the proton. This is something that establishes that neutrons exist, that there are particles with approximately the mass of protons that don't carry any charge. And then finally, nuclei have a magnetic dipole moment, and we can measure that dipole moment, and it's about 1,000 times smaller than the electron dipole moment. But it is meaningful, important to many properties. I've said this, but I want to make it explicit here. Nuclei are made up of what we call nucleons, and the nucleons are just protons and neutrons. And then, as I mentioned earlier, protons and neutrons themselves are made up of quarks. Intranuclear forces, nucleon forces rather, are very short range, of the order of 1 femtometer, and that force drops exponentially with distance. That's the force between, for example, a neutron and a proton, drops exponentially with distance with a decay length of about a femtometer. Forces between nucleons on very short distances are very strong. At 1 femtometer, the force between a proton and a neutron is about 137 times stronger than the electromagnetic force between 2 protons. And actually, the strong force between a proton and a proton would be 137 times stronger than the electromagnetic force. But the strong force falls off exponentially with distance, and the electromagnetic force falls off as 1 over the distance squared. So at large distances, electromagnetic force is much larger. From what we can measure and model, nucleon forces, the forces between nucleons, are only attractive. They're charge independent, and they don't appear to have any charge of their own. There's no repulsion, for example. How do we know what we say we know about the size? Here's an example of an experiment to actually measure the size. The experiment is to shoot electrons into a target that holds a certain type of nucleus, and then look at the diffraction pattern of the electrons as they exit. So let's say that our target rather, we might say is over here, for example, and then we're going to shoot a beam of electrons into that target, and then we're going to take a detector. Don't use your eye. We're going to take a detector, and we're going to rotate that through an angle and measure the intensity of electrons as they come shooting out of the sample. When we observe that intensity as a function of angle, we find that that intensity looks very much like a diffraction pattern. Remember, a diffraction pattern would look like this. The intensity as a function of angle will look like this. This is just a logarithmic plot of essentially the same kind of pattern. So here's the experiment. Electron shot in, measure the intensity as a function of angle, analyze it like a diffraction pattern. And you find that there's a minimum there, and that minimum occurs at the diameter of the object that you're shooting at. The minimum appears at an angle theta, and then we have the wavelength of the thing that we're shooting at the object. So this is the wavelength of the electrons. This is the radius of the nucleus. And that's a simple diffraction pattern, which predicts the position of that minimum. In this particular case, it occurs at about 50 degrees. And that allows us to infer the radius of the nucleus, approximately. The scattering experiment is actually a bit more complicated in that the electron is charged, and the interaction between the electron and the nucleus is due to a 1 over r squared interaction. So we're not going to have a perfect diffraction pattern. However, putting all the physics in, we can model that diffraction pattern, and we find the size of the nucleus from that. And the size of this nucleus is about a femtometer. By the way, there's a little story here, which is that the cross-section, that is the effective area, pi r squared, of a nucleus, when it's actually measured, seems to be much bigger than might otherwise be predicted. Comes out to be 10 to the minus 24 square centimeters for a nucleus. And that was so much bigger that people decided to call that unit the barn, because a barn has a big cross-section. So here is a plot of the charge density in various nuclei as a function of radius, which is determined by that fit to the electron scattering diffraction pattern. So in this model, the electron can actually penetrate the nucleus, all right, and scatter out. And the charge density determines the rate of scattering at various angles as a function of energy for the electrons. And so we can deduce what the charge density looks like. So the charge density for a light nucleus like carbon is rather high in the middle and then drops off, all right? So it's not a continuous charge density. It is continuous. It's not a square charge density where you've just got a simple radius to the nucleus, but there's an effective falling off of the probability of finding protons in the nucleus as a function of distance from the center. And again, that distance is of order femtometers. So that would be our radius for carbon, 2 1/4, 2 1/3 femtometers. As we increase the mass of the nucleus, we see, for example, I don't see what atom this is. All right, oh, calcium 20. All right, the density at the center drops down a little bit, not very much. It drops down a little bit, and the radius becomes larger. And then as we go to heavier and heavier nuclei, the radius moves outward. So we could effectively sort of claim a radius at about half the maximum density for the nucleus. So for carbon, the radius would be that. And for, let's go out here to bismuth, all right, the height is only 0.7, so 0.35 would be in here, and we come out there, and that would be the radius for bismuth, okay? So as the atomic number goes up, the radius increases. That's no surprise. A little bit of a surprise is that as the atomic number goes up, the density seems to decrease slightly. It's approximately the same, right? But it decreases slightly. And then the other thing that we learn is that the charge density, the density of protons, sort of falls off at the edge of the nucleus in sort of a blurry way. It's not a simple square. So again, this result is found from scattering electrons off of nuclei and looking at the pattern of intensity as a function of angle. Okay, once we know a little bit about nuclei, we'd like to have some compact way of describing the nuclei. And there is a standard pattern, all right? Somehow the font came out rather small here. This should be much, much bigger, all right? But we've got, you can get the idea from this, that the superscript on the upper left of the nucleus is what's called the atomic mass number, which corresponds to the number of protons plus the number of neutrons in that nucleus. The nuclear charge, right, is in the lower left, and there's a bit of a redundancy here in that once we've identified an element, for example carbon, then the nuclear charge is fixed. The atomic mass number isn't necessarily fixed. We can have a variety of numbers of neutrons, a variation in the number of neutrons, right? So the atomic mass number can change and we still have carbon. But once we've established that something is carbon, then the nuclear charge must be equal to 6. That's what defines carbon, all right? So sometimes people just tell you what element it is, and then you have to look up the nuclear charge. But they most frequently in particle physics, in nuclear physics, and in nuclear engineering, and even in medicine, they will tell you the atomic mass number or the isotope. One atomic mass unit is defined to be 1/12 of the mass of carbon-12, and there's the actual mass unit to only 4 significant digits in, and it's known to about 6 or more. I'm actually not sure, but at least to 6. The atomic mass unit is defined to be this, and the atomic mass unit is 931.5 million electron volts divided by the speed of light squared. So we can convert between these two by converting millions of electron volts to joules and converting the speed of light to 3 × 10⁸ meters per second. But we most frequently work with this unit. The mass of the proton, and a proton that's loose, not in a nucleus, is 1.00782 atomic mass units, or about 938.3, I think it's 27 million electron volts over c squared. The mass of the neutron is a little bit greater than the mass of the proton. We'll talk about that later on. And the overall mass of the nucleus, as you can see here from the fact that the atomic mass number is only 931.5, is less than the sum of the neutron and proton masses that make it up. The difference is due to the potential energy, due to the strong force that binds the nucleons to one another. When 2 nucleons come together and their total energy is reduced, usually a gamma ray is released. That gamma ray carries away energy, and that reduces the overall mass of the nucleus, making it impossible, by the way, for a stable nucleus to decay to neutrons and protons. A famous relationship is this one, or something to know is this, that the binding energy per nucleon, right, is actually somewhat constant over a very large number of nuclei, all the way from carbon-12 to the heaviest nuclei, even for unstable nuclei that we know. So that binding energy per nucleon is about 8 to 9 million electron volts per nucleon. So if I have an atom, a nucleus with 100 nucleons, then the total binding energy for that nucleus would be 100. Oh, sorry. This is the atomic number here. No, this is the atomic mass. I take it back. So atomic mass 100, then the total energy that's tied up in binding all of the nucleons together would be about 850 million electron volts. We're going to talk about this curve, and we're going to talk a little bit about the variations from the curve in the next few slides. So those are properties. Once we know something about the patterns of the properties, then we can begin developing models to try to understand. And one problem is that a nucleus, typical nucleus, is composed of dozens of nucleons, and we don't know the details, or we didn't when these models came about. We still don't know. We know the statistical details of the structure, but protons and neutrons in nuclei are not static things. They're quantum mechanical objects. So we're forced, if we want to be able to predict and have some understanding of the properties, to come up with sometimes very approximate models. One that works very well and is in a large extent really physically wrong, but it works very well and it's worth talking about because it gives some insight, is called the liquid drop model of the nucleus. This model is empirical, so we look at the data and we just fit the mass data according to certain terms. And I have a listing here for the terms that we're going to worry about, but I'll talk about those later on. Another model, which is more explicitly quantum mechanical, this one here is really not quantum mechanical at all. The liquid drop model, in its simplest form, has no quantum mechanics in it. The Fermi gas model explicitly takes into account the fact that protons and neutrons are fermions, and you can only put two into a given energy state and spin up, spin down, and that determines the actual energetics of nucleons in nuclei. Then a refinement to the Fermi gas model is what's called the shell model. We'll talk about that a little bit later. Again, my point here is for you to understand where these things come from. And then finally, if we really want to dig in and understand the structure of nuclei better, then shifting over to a quark model where neutrons and protons are made up of quarks, and in their interactions, neutrons and protons can exchange quarks and they can exchange other fundamental particles. How do we think about interactions between nucleons? The major force that we will be concerned with in nuclear physics is called the strong nuclear force. The nucleus itself is a bound state of a number of protons and a number of neutrons all bound to one another. The protons and neutrons are made up of 3 quarks each, and quarks themselves obey the rules of quantum numbers we know. But we have behavior that implies the existence of other quantum numbers in addition. The normal properties that we know and that quarks obey are charge, spin, and the spatial quantum numbers that we'll talk about later when we talk about solving the Fermi model. Forces between nucleons include primary force is the strong force. The mediator for that strong force, the carrier, is called a gluon. The electromagnetic force, the carrier for the force, is a photon. And gravitation, the carrier for that force, is taken to be a graviton, but gravitons have not been observed. Neither have gluons, but there's a lot of spectroscopy that tells us about their properties. Some other quantum numbers that describe the interactions between quarks and nucleons are isospin and color, strangeness and charm. We're not going to be talking about that in this portion of this course. The strong force is actually a force between quarks, and it has the strange characteristic that the magnitude of the strong force increases with distance up to about 1 femtometer. That's quark-quark interactions. And then it becomes constant after that. And the actual strong force between a proton and a neutron is actually analogous to forces between atoms in a molecule. So if we have 2 atoms, each of those atoms are neutral, but they can exchange electrons and they can exchange photons, and that exchange induces electromagnetic interactions between the atoms. And so the interactions between nucleons is similar in that as far as color charge is concerned, protons and neutrons are neutral, but they can exchange particles and that can induce a force between them. And again, that force has the characteristics that we described earlier. It decays exponentially with distance because it's the leftover force. Decays exponentially with distance, and the range is approximately a femtometer. So now our first model. We think of the nucleus as a sphere that contains the nucleons. In this case, we've colored the protons red and the neutrons white. And every nucleon in the nucleus, there's no fixed structure to the nucleus, but every nucleon in the nucleus has a certain number of near neighbors that are less than a femtometer away. So they're pulled together. Right? And on average, in a very heavy nucleus, each interior nucleon has about 12 nucleons surrounding it at a distance of less than a femtometer. So if we think about what the total energy might be, or even the average per nucleon might be, if we think of the nucleus as essentially being a constantly mixing drop, liquid drop, of protons and neutrons, and you can think of them as physical, not quantum mechanical objects, physical objects that just sort of jumble around, right? And so on the average, each nucleon has 12 neighbors, and there's a strong force with each of the 12 neighbors, and that leads to the binding energy, okay? The so-called volume term represents the strong binding force between the adjacent nucleons, and because on average each nucleon has about 12 neighbors, we can determine that the total strong force energy due to neighbors, it would, to first order, just go up with the number of nucleons to the 1/3 power, because we're looking at how many neighbors they are. And as a result, or rather, the total energy goes up as the number of nucleons, because each nucleon has the same binding to its neighbors. And we call that the volume term, because we're just counting up how many nucleons and we're assigning a binding energy to every nucleon in the structure. The so-called surface term is a correction, because if you look at this, and if I said, for example, in this case, I might claim that every nucleon has 6 neighbors. Well, they don't all have 6. If you start looking at it, they don't have 6 near neighbors. But in particular, the ones that are out at the edge here have fewer neighbors. This one here has 1, 2, 3 neighbors, rather than the 6 that we can see in 2 dimensions here. So the surface term is a correction due to the fact that not all nucleons have 12 nearest neighbors. So this one's going to be subtracting from the total energy here, because not all of them have neighbors. Then the next term that we might consider is the average distance between charged protons, because they'll repel one another. On average, they're going to try to get further apart, right? But they have to be binding, and they prefer to be bound to neutrons. So they're trying to get further apart, but they can't get completely out to the edge, because then they'd be adjacent to one another around the edge. They're spread throughout the structure. And that force drops off as 1/r². So it turns out that that Coulomb term, which is a correction due to proton repulsion, doesn't drop off as quickly, and we'll talk about the consequence of that. Then there's an asymmetry term, which actually comes out of thinking of neutrons and protons sitting in Fermi wells, and then if the number of neutrons and the number of protons is not equal to one another, then one of the 2 wells is filled a little bit too high. There's a correction to that we're going to talk about in a little bit. And then there's a pairing term because each type of nucleon is a fermion and they like to sit in the lowest state that they can, which would put 2 spins into each state, 2 protons into a particular quantum mechanical state. So in terms of equations, to actually solve for the total binding energy, I've written it out here. This term with A1 is proportional to the number of nucleons because the number of nucleons is proportional to the volume. So the first term is the binding energy per nucleon. It comes from the total number of nucleons binding to one another. The A2 term, which is negative, right, subtracts from the total binding energy where we've assumed that every nucleon has the same number of neighbors. And then it says, nuh-uh, the neighbors on the surface, the nucleons on the surface have less binding energy, so let's correct for them. And as a result, that correction is proportional to the surface area. So the atomic number is proportional to the volume. It is atomic number to the 2/3 gives us the approximate number of nucleons on the surface. The third term is the nuclear repulsion term. And on the average, the protons are a certain distance apart, which depends upon the radius, and the radius depends upon the atomic number, the atomic mass number to the 1/3 power. So this is the Coulomb repulsion correction. It's negative as well for the binding energy. And then we have the 2 other correction terms, which we're not going to dig in at this point, So that's actually the liquid drop model, and that liquid drop model predicts that curve of the binding energy per nucleon very accurately. Just those 3 terms actually corresponded to the line through the data points that you saw on the binding energy graph. So what's the next level of approximation, or perhaps trying to understand better what's going on in the nucleus? And it's one in which we assume that the protons make up Fermi gas, and neutrons, which are different particles, make up a Fermi gas. Protons and neutrons are attracted to one another, forming an overall potential well for protons and neutrons to be inside the volume of the nucleus. So that's the model. And then we calculate what the quantum levels are for a deep spherical well. And in the simple Fermi gas model, we ignore Coulomb repulsion between the protons and just go ahead and calculate the energy levels of protons and the energy level of neutrons. So here's the model. I'm going to run through the solution here, but I'm not going to go into the details. We assume that the nucleus is an object of radius A with a potential of 0 at its center. And in the simplest model, outside of the nucleus, we set the potential for protons and for neutrons equal to 0. So this is the simplest model. So the Schrödinger equation that we solve on the inside looks like this, where u of r is actually radial distance times the wave function as a function of radius. All right. So u of r is actually a product already. And u of r is taken to be 0 outside, and we can solve for it inside for a given angular momentum. Here's the solution to the 3-dimensional time-independent Schrödinger equation in spherical coordinates. In general, We solve this equation by separating variables. And here I mentioned that u is the product of r times the actual wave function as a function of radius, so that's what I've got in here. We solve it in the way that you've done already, by separation of variables, and we end up with angular momentum, and the solutions for the angular momentum portion, the theta and phi portion, are identical to what we did for the Coulomb potential, because those solutions actually don't only depend upon the fact that the potential is spherical, central. The simple model energy levels for example, protons as a function of angular momentum and a principal quantum number look like this, right? So for L equal to 0, angular momentum equal to 0, the energy levels correspond to these numbers here, where those can be associated, given the radius, with actual energies. E prime is in units of h bar squared over 2 times the mass of the nucleon times the radius of the nucleus squared. So we have an energy scale here, and then we have angular momentum here. The n equals 1 states, there we go. N equals 1 has only one angular momentum state, angular momentum 0. N equals 2 has two angular momentum states, 0 and 1, right? And unlike the Coulomb potential, different angular momenta have different total energy. But this sets up a way for us to understand what energy levels a proton, for example, could go into, or a neutron could go into in the nucleus. If we actually go through and make estimates of what those energies are for a radius of about a femtometer, I don't remember the exact number, then we find energy levels for the nucleons in a square well model nucleus, infinitely deep square well, measure from the bottom of the well, correspond to these energies here for the radius that we know. And you can see that the scale of these energies, because the nucleus is so small, is in millions of electron volts. So here's a schematic of what the energy levels for protons and neutrons in a finite square well might look like. The n equals 1, n equals 2, L equals 1, n equals 2, L equals 0. So those might be the sets of levels, and to each energy level that we solve for with those quantum numbers, we can put a spin up and a spin down. In the simplest Fermi gas model, the energy levels of protons and neutrons are nearly identical to one another because they have nearly the same mass, and they just go into the potential that is the nucleus without regard for other than the fact that there are strong interactions that form the potential well. What does it actually look like for a heavy nucleus? All right, these are the result of measurements that can be made, and what we find is that for two reasons. Because neutrons don't repel one another and therefore don't have a Coulomb repulsion, right, the way that protons do, that neutrons experience a well which is deeper than the proton well, because the protons repel one another, and that raises the bottom of the well. Again, this is a very simple model. And for tellurium-125, the depth of the well fitting to these energy levels corresponds to 43.6 million electron volts. So it's a finite square well. For neutrons, and for protons, it has a depth of 38.2 million electron volts. This is not exactly to scale. It's just an idea. And then we can solve for the energy levels within that square well, and those are our actual calculations of energy levels within the square well. Now what we do is figure out how we can get 125 nucleons where the protons and the neutrons sit at the same energy. Their Fermi energy has got to be the same. If it's not the same, then it would turn out that the total energy of the system is higher than it would be if these two are not the same. So than it would be if these energy levels were the same. Okay, the depth from the vacuum to the top of the Fermi level the highest energy neutrons in the system is about 6.6 million electron volts, and the distance from vacuum to the most lightly bound protons in the system is about 8.7 million electron volts. So we can determine that by actually shining gamma rays into the system of greater than that energy and then observing protons being injected. So it's like a photoemission experiment for protons. So we make up our well of a certain depth. We make a square well of a certain radius, of the measured radius, and then just solve the quantum physics, and actually the energy levels that are observed correspond pretty well to the actual energy levels. So again, this is experimentally tested. The next correction to that simple Fermi model is called the shell model. And in the shell model, we take into account the fact that the density of the nucleus changes as a function of distance from the center. And as a result, we should actually make the boundaries of the well not square, but varying slowly from inside to outside. And the way that this is actually modeled is to make the well that we observe to be approximately the combination of a harmonic oscillator and a square well. So those are the two parameters that go into fitting this, right? That's still not quite good enough. It turns out that we need to add spin-orbit coupling into the problem, and that changes the shape of the well somewhat. But that's as much as we're going to talk about for the summary of the properties of nuclei at this point.